Okay. So, just we have seen that your V0 ut, that we have explained already how it can be represented. This is V0 into ut, it is right, and step unit function we have given for t less than 0, that ut is 0, and it is, if it is greater than 0, then t greater than 0, then ut is 1. So, that means when the switch in this position, just we have explained, 1 and 2 are short circuited, that means your V12 is equal to your output voltage whatever it is, that is 0, right. And that is your, and second thing is, if switch moves from this position to that position at t is equal to 0, then at that time your what we call V12 is equal to V0, that is Vt, right, is equal to V0. So, this is all have been explained here. Similarly, for the current source, if you take, I mean, suppose you take a current source, that I0 ut and its equivalent circuit is shown. This is I0 into ut. So, we have explained the step unit function, that for t less than 0, that is your ut is equal to 0, and t greater than 1, t greater than 0, that ut is equal to 1. So, when switch in this position, whatever shown in this figure, at t is equal to your g, or what you call, it is switch is open at t is equal to 0, but when switch is in this position, that is t less than 0, in that case this is open, that means your it is equal to 0, right. And as soon as switch moves from this position to that position, I mean, if the switch is moving from this to that, that means if it is connected here and it is not there, at that time it is equal to I0, right. So, this is your, this is the meaning of I0 into ut, right. That means for t less than 0, your what you call that your ut is equal to 0, and t less than t greater than your 0, that your what you call that ut is equal to 1, that unit step function. So, this is I meaning of, when you will solve the your what you call that your transient problem, at that time we will consider this kind of source such as V into ut or I into ut, we will see later, right. So, this is your meaning of I0 ut is like this, right. So, that is the idea, that rather than moving like this, if we represent circuit, if we represent the source, voltage source or current source, right, by multiplied by unit your step function, how when we will solve the circuit, at the time we will know how it behaves, right. So, this is your, now I am clearing it. So, this is your representation of current source. Now, next is that unit impulse function, right. Actually, physically unit impulse function is like ideal sources, voltage ideal sources or resistor, that your unit physically it is not realizable, but it is a very strong mathematical tool, right, for circuit analysis. So, the derivative of the, it is underlined only, the derivative of the unit step function ut is the unit impulse function. Now, mathematically it can be expressed as delta t, we represent delta t or what you call that unit impulse function, right. So, it is unit impulse function. So, delta t is equal to d dt of ut, it is equal to 0 for t less than 0, it is t is equal to 0, it is undefined, right, and t greater than 0, again it is 0, right. So, this is actually what you call, this is the definition of unit impulse function, right. So, it is also known, sometimes we call as a delta function. In a book you will find this unit impulse function also is termed as delta function, right, and is shown in figure this one. This is t and this is, say it is 0, time 0, and this is delta t. This 1, if you will find it is marking 1 means its unit area is 1, right, that is strength. We will see later much after that, right. It, so, but this is your what you call unit impulse function, the representation, right, and this one we will see later, it is unit area, it is called the strength of the your unit impulse function, we will see just after few minutes. So, impulsive voltage and currents occur in electric circuit as it is. I mean if you might have experienced also that impulsive voltage and currents occur in electric circuit as a result of switching operation or impulsive sources, right, like ideal sources, ideal resistor etc., right. The unit impulse function is not physically realizable, right, but it is very useful for mathematical tool. So, that means physically it is your what you call, it is not your realizable, but it is a very useful mathematical tool, right, for analysis of various circuits. So, just let me clear it. So, the unit impulse may be regarded as an applied or resulting shock and visualized as a very short duration pulse of unit area. Mathematically, actually we can express this, that your integration just before switching, that is 0 minus to 0 plus delta t dt is equal to 1. Its area is what we call, it can be mathematically it can be expressed as 0 minus to 0 plus delta t dt is equal to 1, right. This is unit impulse function, but its area is 1. T is equal to 0 minus time just before t is equal to 0 and t is equal to 0 plus time just after t is equal to 0, right. So, you have to remember this, that from 0 minus to 0 plus delta t integration of delta t dt is equal to 1. This is equation 35. But to this reason, it is customary to write 1 denoting unit area, 1, that figure I told you here, right. It is in this figure here I told you that it is 1 means it denoting your unit area. So, but see how is it? Due to this reason, it is customary to write 1, that is denoting unit area, as in figure 30 I showed you. The unit area is known as the strength of the impulse function, and when an impulse function has a strength other than unity, the area of the impulse is equals to its strength, right. So, actually area of the your what you call unit impulse function, that is actually strength. I have underlined here for you, underlined here, right. So, for example, an impulse function, say here just here, an impulse function like 8 delta t has an area of 8, right. Similarly, your what you call an impulse function of 4 delta t plus 2, 8 delta t and minus 4 are shown in here, like. So, this is 8 delta t. So, it is delta t. So, it is, this is the time 0. So, it is 8, you can write this is 8 delta t. Now, for 4 t for delta t plus 2, that is t is equal to minus 2, right. So, it will start from here, this is 4 delta t plus 2, it is just a impulse response, right. And similarly, it is minus 4 delta t minus 2. So, t is equal to 2 and it is minus. So, it is minus 4 delta t minus 2. This is the representation of the impulse function. In this case, strength is 8, in this case strength is 4, in this case also strength is 4, right. So, let me clear it. So, this is 3 impulse function I just showed you. So, impulse function affects other function, and to illustrate this, let us evaluate the integral. I mean, it affects that impulse function affects the other function also. For example, you take you take that integration alpha to beta f t delta t minus t 0 dt, right. Now, t 0 is lying in between alpha and beta. Since delta t minus t 0 is equal to 0 except at t is equal to t 0, because at t is equal to t 0 it is undefined, we just saw, right. There it was delta t, t less than 0, greater than 0, whatever is given 0 0, but at t is equal to 0 it is undefined, but there we are taking delta t minus t 0. So, it is 0, but except at t is equal to t 0. So, the integrand is 0 except at t is equal to t 0, because it is undefined. Therefore, alpha to beta f t delta t minus t 0 dt you can write at t is equal to t 0, you can write because at t is equal to t 0, right, except at this delta t minus t 0 is equal to 0 except at t is equal to t 0. Therefore, at t is equal to t 0, alpha beta it is f t 0 delta t minus t 0 dt, or is equal to, it is f t 0 will come out, it is here, right. Then integration your alpha to beta your delta t minus t 0 dt, just let me go little bit up, right. So, here now this has come out, right. So, alpha to beta delta t minus t 0 dt is equal to f t 0, because this is actually you take that area is equal to your what you call that unity 1, right. So, that is equal to f t 0. Therefore, alpha to beta f t delta t minus t 0 dt is equal to f t 0. So, this is equation 36, right. That means, let me move little bit up. That means that this equation 36 actually this is your equation this is your equation 36. It clearly shows that a function is integrated with the impulse function. We get the value of the function at that point where the impulse occurs, right. This property of the impulse function is very useful and known as the sampling property or shifting property, right. So this is very important. So but in this course we will study little bit only, right. More things are available in a course like your signals and networks, right. That is a different thing, but here just little bit we will learn. So let me clear it. Now therefore consider a special case for t0 is equal to 0, then equation 36, that means this equation, if t is equal here it is, if t0 is equal to 0, here it is t0 is equal to 0, if t0 is equal to 0, then it will be say in between 0 minus to 0 plus f0 delta t dt is equal to f0. So here similarly, that means if t0 is equal to 0, then it will be 0 minus to 0 plus integration ft dt delta t dt, and that is f0, because this one just I am making it, this one is equal to your f0, then integration 0 minus to 0 plus delta t dt, right, and this part is unity. So it is become f0, right. So let me clear it. So this is all regarding impulse function. This is just for the sake of completeness of this thing, just I have taken this, right. There are many other singularity function, but we will come up to ramp only and some example. So unit ramp function, in this case unit ramp function RT can be obtained by integrating the unit step function ut. If you integrate unit step function ut, you can write RT is equal to your minus infinity to t ut dt is equal to t into ut, right. So RT is equal to actually 0 for t less than equal to 0, and RT is equal to t for t greater than equal to 0, right. That is why minus infinity to t ut dt is equal to t into ut. This is equation 38. This equation can be written like this, that RT is equal to 0 for t less than equal to 0 and is equal to t for t greater than equal to 0. This is equation 39. This is that your what you call, it is integration of the unit step function, that is your what you call unit, or if you just want to obtain unit ramp function. So a ramp is a function that changes at a constant rate, right. So basically it is equation of straight line. So the unit ramp function, unit is 0 for negative values of t and has a unit slope for the positive values of t. So figure 32 shows the unit ramp function. That means for a negative value of t, it is plot like this. It is plotting like this. So negative value of t, it is 0, and for positive value of t, it is shown, right. And this is unit, this is also 1, right. So this is a unit step, your what you call the ramp function. So next, the unit ramp function may be advanced or delayed, right. Previously also if in t0, right, it may be advanced by time t0 or delayed by time t0. For the advanced unit ramp function, right, this is for advanced rt plus t0, that is if it is 0 if t less than equal to minus t0, and it is t plus t0 if t greater than equal to minus t0. This is equation 40, right. So if you plot it, right, so shows the advanced unit ramp function. So rt plus t0, so it will here it is your t plus t0, t is equal to minus t your t0, and this is your minus t0 plus 1, and this difference, I mean only distance, this difference actually it is 1 in terms of just length, this one, and this is also 1. So this height is also 1. So your what you call slope is also 1. This is you call that advanced unit ramp function. This is advanced unit ramp function, right. And this point is minus t0 plus 1. So it is minus t0. If you take this side, negative will come, but distance is 1, minus t0 minus your t0 plus 1, right. So it is basically minus t0 plus t0 minus 1. So this will be cancelled, minus 1, because it is on the negative axis of the negative side of the time axis, but distance is 1, right. So let me clear it. So this is your unit ramp function advanced by t0. Now if it is delayed, if if it is delayed ramp function, then it will be RT minus T0, right. I mean it is equal to 0 for t less than equal to T0, and it is T minus T0 for t greater than T0, right. So this is the figure 34. So the delayed unit ramp function, this is your delayed unit ramp function, right. So it is starting from T0, and this distance again, this distance is again 1, right. T0 plus 1 minus T0 1, and this is 1. So unit ramp function, and this is RT minus T0. This is the plot of your what you call unit ramp function delayed by T0. That means when it is delayed, it will be t is equal to T0 on the right hand side, that is the first coordinate, right. And when you are that is starting from here, but this is your this be less than T0, it is 0. Similarly, when it is advanced, it is starting from somewhere at t is equal to minus T0, right. So this is your unit ramp function delayed by T0. So next is, so although there are many more singularity functions at this point, but we in this course we will just for the sake of completeness little bit just we have given the flavor of these 3 different functions, right. We are only interested in impulse function, unit step function, and the ramp, right. Note that 3 singularity functions, impulse, step, and ramp, are related to differentiation as follows. So if you look into that your delta t is your differentiation of dut by dt, right. Similarly, ut also is differentiation of ramp function drt by dt, right. Or by integration ut will be minus infinity to t delta t dt, right. And similarly, for ramp function rt is equal to minus infinity to t ut dt, right. If you this is delta t is equal to differentiation of ut, and ut is equal to differentiation of RT, but other way if you integrate, ut will be your minus infinity to t delta t dt, and RT will be minus infinity to t ut dt. This is 42 and this is equation 43, right. So next, take a 1 or 2 simple example. It is given that express the voltage pulse, right, in figure 35, this is figure 35, in terms of the unit step, determines its derivative and sketch it. So it looks like it is a gate function, actually it is a gate function. Actually at time t is equal to 3 seconds, actually idea is like this graph is like this. So it is a voltage pulse. So at time t is equal to 3, it is switched on, and say time t is equal to 6, it is switched off, right. So it is a gate function. So that means you have to see that this voltage, this is Vt, and this voltage is 10 volt, right. So Vt basically it is a function of your what you call unit step function. So at t is equal to 3 seconds, say it is switched on, and t is equal to 6, it is switched off, and it is a gate function. So how we will get it? Let me clear. So all these things are written for you, right, whatever I am telling. So it is a gate function. So what I said, at 3 seconds it switches off, and at 3 is equal to your 3 seconds it is switching on, switches on at t is equal to 3 seconds. Here it is switches on at t is equal to 3 seconds and switches off at t is equal to 6 seconds. That means it consists of sum of 2 unit step function as shown in figure 36. So let us see how is it. So now when it is switching on, its value was given 10 volt Vt, right, say 10 volt. So when it is switching on at t is equal to 3, so this will be actually 10 ut minus 3, right. And when it is switched off at t is equal to 6 seconds, it will be minus 10 ut minus 6, right. So at the time of switching on, it will be 10 ut minus u3, right, plus, and at the time of switching off at t is equal to 6 seconds, it will be minus 10 ut minus 6. Now if you that means this function, actually this gate function actually is equal to sum of 2 unit step function, that is this one plus, the one plus symbol is here, I have made it plus, right, is equal this one. That means this one, that means mathematically if you write like this, it will be 10 ut minus 3 minus 10 ut minus 6, because it is this one plus this one. This function this function, that is figure 35, this function is equal to this function, these two unit step function, these two or what you call step summation of these two step function. So in this case, this is the decomposition of the gate function, this one and this one. So if you represent now Vt is equal to, it will be 10 ut minus 3, that is your this one, minus 10 ut minus 6. That means it will be 10 ut minus 3 minus 10 ut minus 10, you take common, ut minus 3 minus ut minus 6, right. This is your representation of Vt, that gate function. And if you take the derivative of this one, dv by dt, if you take the derivative, it will be your delta function, that is your impulse function. It will 10 delta t minus 3 minus delta t minus 6. Here we have seen no, this one, that your what you call delta function is equal to your derivative of u, right, and a unit step function is derivative of the ramp, right. So if you take the derivative of this one, if you take the derivative of this one, this will be dv by dt is equal to 10, it will be delta t minus 3. If you take the derivative of unit function, it will be your delta function, delta t minus 3 minus delta t minus 6, right. And now if you sketch your dv by dt, so it is a delta function. So at t is equal to 3, its strength is 10, so it will be 10, and at t is equal to 3 seconds it is plotted. Another thing is that t is equal to 6, but it is minus 10, it is t is equal to 6, it is minus 10. So this plus 10, this is minus 10, it is plotted, right. So because it is 10 into delta t minus its strength is 10, right. So this is how one can plot your what you call that your gate function, and this is the things are very simple. Let me tell you, things are very simple. So another one will take things like this figure, it shows a sawtooth function, express this function in terms of singularity function. It is a sawtooth function is given, right. So it is basically a ramp function, and your another thing is that it is a gate function, right. So it is its slope, this height is 12, right, and this is from here to here it is 3. So its slope is equal to your 12 by 3 is equal to 4, the slope is equal to 4 for this straight line, right. Now let me clear it. So how will represent this one, how will represent the Vt, right, let us see. So a close observation reveals that Vt is multiplication of a ramp function, it is a ramp function, and another thing as a gate function and a gate function, and this at t is equal to 3, suppose your what you call at t is equal to 3, it is your what you call that your it is going on a ramp, and at t is equal to 3 it switches off, right. So a close observation of figure 38, it reveals that Vt is a multiplication of a ramp function and a gate function. So slope of the ramp function is 4, I told you it is slope of the ramp function is 4, therefore Vt will be that they or what you call it will be 4t, then it will be ut minus 3, right. This way you can write, because slope is 4 and it is a product of ramp function and a gate function, right. So it will be slope is 4, so it is a ramp function, basically it is a straight line passing through the origin, right. So that means your this equation of the straight line will be your what you call Vt, for this straight line only Vt is equal to 4t, right. And then that means we can represent 4t ut and minus that your ut minus 3, suppose at this point it is switches off. So 4t ut minus 4t ut minus 3, right. So in this case this one, I mean it is understandable to you, right. The slope is 4, equation of the straight line is 4t, and at t is equal to 3 seconds, suppose something is switched off, then it will be your 4t ut minus 4t ut minus 3, right. So that is your 4t ut minus 3. So multiply this, so it will be 4t ut minus your 4t ut minus 3. Now this one, this t we can write it is t minus 3 plus 3, right. This is equal to, you can write this is 4 RT as it is. So minus 4 t minus 3 into ut minus 3, and this is minus plus minus, so minus 12, it is ut minus 3. So it is 4 RT minus 4 t minus 3 ut minus 3 minus 12 ut minus 3. that is equal to, this is 4 RT ramp function minus 4 R t minus 3, that is your advanced or delayed we have already shown in the ramp function, right. So, minus 4 R t minus 3 minus 12 u t minus 3. So, this is the answer, right. This is little bit before moving to the your step response of an RC circuit considering some sources. So, little bit particularly voltage source, when we will apply when we will solve those circuit, little bit idea is required. So, that is why. So, this is a simple thing, and I told you how to break it. Little bit problem, not much problem we will study on this, but just to give you some ideas. That is why we have made it like this, some example, right. Other singularity function we will not consider in this course. This is just little bit of basic, right. So, next is step response of an RC circuit. Now, the step response is the response of the circuit due to sudden application of a DC current or voltage source, because our interest here is DC transient, and that is first order circuit, either RC circuit or RL circuit, right. So, in this course we will not consider RLC circuit or LC circuit, that is second order circuit, we will not consider. So, the step response is the response of the circuit due to sudden application of a DC current or voltage source. So, figure 39, this is your figure 39, right. It shows RC circuit where Vs is a constant DC voltage source. This is actually your RC circuit, this is RC circuit, and Vs is a constant voltage source, and one its capacitor is there. It may be initially charged, may be initially uncharged. So, at your for t less than 0, the switch was open, and at t at your what you call at t greater than 0, the switch is closed, right, 0 minus or 0 plus. Just before switching it is 0 minus, and just after switching it is 0 plus, right. So, switch is closed, right, for t greater than 0. So, this circuit, this is the circuit, and this can be represented as, this is an RC circuit, this can be represented as, that is Vs ut, that is source voltage is this is your what we call, the switch is closed, and it can be written as Vs ut, then R and C. Actually, idea is simply like this: for t less than 0, we know the unit step function. For t less than 0, ut is equal to 0, and for t greater than 0, ut is equal to 1. So, when it was t less than 0, this voltage source is completely disconnected, right. So, nothing is flowing in the circuit. So, in that case ut is equal to 0. So, here also if your ut is equal to your 0, and for your t greater than 0, right, your ut is equal to 1 when switch is closed. That is why this can be represented, this circuit can be represented as like this, Vs into ut, right. Earlier we have seen that step function, unit step function, right. So, that means that an RC circuit with voltage step input, right. So, basically it is a voltage step input. I mean from here when it is open is okay, but as soon as you close the switch, as if it is going as a step input. So, that is why it is that your circuit of figure 39 with voltage step input Vs ut, and this is the current IT, this is the current IT, right. So, before moving further, just one thing, that current direction I have taken like this. Suppose if you take a your what you call that node like this from here. First let us see what is IT. You apply KVL. So, it will be R, then IT moving like this clockwise, right, your plus your V, right, and minus Vs, right. Vs ut you can write, but for t greater than 0, if t greater than 0, then ut is equal to 1, right. So, that means your it will be RIT plus V mine is equal to your is equal to 0, right. That means my IT will be is equal to your this Vs minus V divided by R, when for t greater than 0, when switch is closed, ut is equal to 1, right. So, that means IT is equal to this direction. If you take current direction is like this, then this one will be V minus Vs, just it will be reverse, it will be V minus Vs upon R. This is the current, and this side, I mean this current, if we take say say I1, and this side if we take, this is your basically I1, right, is equal to minus of IT, T I am not putting here, if you want you can, and this side you say IC, right, that means my IC is equal to C into dV by dt, right. That means at this point, suppose this node is A, suppose you create like this and apply KCL at this point. So, that means my I1t, rather I1 I can make I1 plus your IC is equal to 0. That means my this is V minus Vs divided by R plus C into dV by dt is equal to 0, right. Although direction is taken like this, but if we apply KCL, say at this point you take, and this direction, in this direction the current is this. So, when you change this direction, suppose this way, it will be V minus Vs, and for t greater than 0 ut is equal to 1, it will be Vs, right. And that means from this equation we have to try to solve this RT. Thank you very much, we will be back again.